12. So almost a year lecture has been going to be complete today. We started in October 2020. This particular lecture series in collaboration with GCRF Clean Environment and Planetary Health in Asia. We call it as CEPHA network, and our Department of Civil Engineering, IIT Madras, and many collaborators in Asia and within the country. So air quality management lecture series started in October 2020. It is a first of its kind in India, which serves an important forum for particularly the young researchers, scientists, engineers, educators, practitioners, now the policymakers, to learn latest achievement or advancement in theories, technologies, applications in the area of air quality management. As I told you, we are organizing this lecture every month in collaboration with GCRF-CEPHA network and Indian International Conference on Air Quality Management. So we have eminent speakers already gave the lecture earlier in the last couple of months. Last lecture was from an industrialist. Now we have with us Professor Schlink, and he is going to give the 12th lecture of this air quality management lecture series. And if you look at it, all of them are significant contributions to air quality management. So now I'll request Ms. Gopika to introduce Professor Schlink. I welcome Professor Schlink. Professor Schlink is an mentor, advisor, and a collaborator, researcher, friend, and we work together in various research projects. I'm very happy to and glad to, he has accepted our invitation for air quality management lecture series 12. So, Gopika, could you please introduce Professor Schlink?
Yes. Good evening, everyone. It is my pleasure to introduce the speaker for the day, Professor Uwe Schlink. Professor Schlink is the Senior Scientist at the Department of Urban and Environmental Sociology at the Helmholtz Centre for Environmental Research, UFC, in Leipzig, Germany, and leads the working group on urban climate and personal exposure. He holds a PhD in meteorology and teaches at the Institute of Meteorology, University of Leipzig. He is also an adjunct faculty at the Department of Civil Engineering, IIT Madras. His research interests include urban air quality, urban climate, climate change adaptation, indoor air quality, statistical modeling, and environmental health effects. Today's talk is titled Individual Worn Sensors Assessing Personal Environmental Exposure, where he will be discussing important aspects of multifactorial personal exposure assessment taken by volunteers. The presentation addresses different concepts for personal exposure assessment, need for standard operating procedures, methods to upvalue the sensor recordings, etc. Sir, we welcome you.
Over to you, Professor Schlink, and welcome to Air Quality Management Lecture Series.
Thank you very much, Professor Shivanagendra, for this warm welcome. And I try to switch to my slides here.
Oh, you can share now. I closed it.
Can you see my screen?
Yes, we can able to see your screen.
So thank you very much, and good afternoon, everybody. And I'm very grateful to the organizers of this lecture for their invitation. I'm glad to have the opportunity to present some of our problems and perspectives, especially for small mobile environmental sensors. And so we discuss several aspects during the next hour. And to introduce this subject, I think you know that there are currently many types of wearable sensors. For example, health trackers that you can wear and on your arm and that measure the heart rate or some parameters useful for physical training. or for example, GPS trackers that you can use for hiking. The wearables we are interested here are applied for environmental measurements, that is for air quality primarily, and for climate parameters, for noise, and for radiation. So the structure of my lecture includes the motivation and the problems important with such sensors, some technical information, the aspect of accuracy of the sensors, and also some concepts to make these measurements, and I will discuss with you some applications. These wearable sensors connect very different disciplines of the science. They connect the information science, the computer science, technology, environmental science, and also public health and behavioral psychology. And of course, urban planning can heavily benefit from such type of monitoring of urban environmental conditions. On this photography here, I hope you can see it. You see a study participant who carries a small pack of sensors here on his back, and he moves around the city by bike. Other people can carry sensors at the upper arm, or they measure during particular activities, for example, during commuting or even during the entire day. So we start with the problems. What problems are what problems require the use of such sensors? And I think you all know that there's a population growth worldwide, and the urban cities they become more denser, they are densified, and you have more emissions, and you also have the climate change. And this modifies the dispersion conditions. So we have the first problem, that is urban regions suffer from increased pollution. And the monitoring networks that are implemented in cities, they are available only in large cities, and they are mostly very sparse. So you have just very few monitoring stations in the city, but you cannot they cannot register the exposure and the pollution directly at the person. Another problem is that in the population there are many chronic diseases for many, many years, like cancer, diabetes, allergies, and they are chronic diseases, not only infections like the COVID currently, but you also have epidemics of chronic diseases. And there was the expectation and the hope that the sequencing, excuse me, that sequencing data of the human genome can provide explanations for these diseases, and that this can suggest methods to cure the diseases. But this expectation was not fulfilled. Epidemiologic evidence points to the fact that environmental conditions contribute at least 80 to 90% of the attributable risk for cancer and degenerative diseases. And this is illustrated in this plot here. So you have the genetic risk is just about 10%, but the environmental risk is very, very high. And at the moment, we know a lot about the genome, but so much data of the exposure of individuals is not available. So recognizing this disparity in the current knowledge between the genes and the environmental exposures, about 10 years ago, Christopher Wilde defined the term exposome. It represents all environmental exposures, including those from diet, from lifestyle, and from all endogenous sources. And here you see some pioneering papers about the exposome concept. And these factors include the external exposure, this coming from outside of the body, but also the internal exposure. So these are the metabolites in the digestive system and in the liver and anywhere in the human body. And as you can see, the external exposome includes the pollution, infections, lifestyle, stress, radiation. So you have many components of the exposome. So the new concept is that in addition to the genome, an important factor for health is the exposome, and we have to measure this exposome and how to register this for further research. The concept of the exposome does not only distinguish the different factors, but also the totality of the exposure during the full life. This is represented in the picture here below. So from the birth or from the prenatal period until the end of the life, there's constantly varying exposure, and this is important because there are specific time periods in your life when we have an increased susceptibility and vulnerability to certain exposure factors. So far, there are nearly no data available about this totality of exposure. There are just simple initial approaches to characterize this exposure. So Exposomics has to take into consideration the lifelong complex exposure of individuals. Secondly, the chemical substances are metabolized in the body. There are new substances, so we have also an internal part of the exposome. And so the exposure is essentially determined by the air pollution, by indoor air conditions, and also by, for example, importantly, by nutrition, drinking water. And the dynamics and the complex interaction of all these compartments must be studied in a more targeted manner, and this is called exposomics. And here different techniques for exposure research are discussed. And the point where our contribution comes into the play is here that we can have mobile devices, and they register the concentration of air pollutants. They, for example, with an accelerometer, they can register the activity of the individuals. And this is also combined with questionnaires asking for behavioral parameters, and also it can be connected to environmental modeling. So consequently, there are following research questions. We ask how to measure a person's multifactorial external exposure, and with specific conditions. That means directly at the individual. It needs to be made in high resolution in space and time, and we should be able to register very low concentrations. And of course, the application of smart information technologies is advisable. So our solution is that we use such wearable sensors Again, here's this picture of the study participant with a back, with a pack of sensors on his back. And in the upper picture, you see our previous sensor collection, a set of different sensors that are combined. And we will discuss these measurements now in the next minutes. So our research tools are wearable sensors. They can register the multifactorial personal exposure of individuals in vivo, directly where people live. And on the other hand, they can explore urban regions. So when people move around the city, they explore the city and they measure the environmental quality in different regions of the city. So this is called citizen science. And these measurements are also often called anthropogenic opportunistic sensing. These smart sensors we apply and we would like to further develop and improve. They function or they have two different functionalities. On the one hand, they measure the environmental parameters, but on the other hand, they also provide the data processing, data storage, data transfer to workstation. So some technical information about the environmental trackers. They can register, for example, noise. They can register air temperature, humidity, light and radiation, and of course, a large number of air pollutants like particulate matter, nitrogen oxides, ozone, and so on. And we also have the GPS for spatiotemporal recordings and accelerometers registering the activity. And so we have information about the activity and the behavior of the individuals, of the volunteers that measure. It is important that the sensors are ventilated and protected against sun. Many of the sensors are sensitive to perturbations from other signals. So this is important that they are protected. And when you imagine that you move with a sensor a longer distance, during this movement, the sensor makes measurements, and we will discuss this later more in detail. Then I think it's clear that passive sampling is not useful to explore the urban region. It is useful when you would like to register the cumulative exposure of a person, but when you would like to make highly resolved spatiotemporal measurements, and passive sampling is not useful, and active sampling is much more important and much better. These sensors should be very small, and so miniaturization is important, and they should have low power consumption. And so these sensors, of course, always demand for regular calibration, that you have accurate values in the records. And due to contaminations and aging of material, there are a lot of inferences that disturb these parameters. For example, mixtures of different gases, or changing environmental conditions like strong heat or strong humidity. And most of these smart wearable sensors suffer from limited accuracy. And the precision and the accuracy of this sensor is a particular subject that we will discuss later. And for an assessment of the person's vulnerability, there are also additional data important, like age, gender, pre-existing diseases, movement behavior. And all these data should be also gathered with the, in combination with the sensors. But I will give an example later. As we are in particular interested in air pollution sensors, I just would mention some technical facts about the different sensors. For example, for particulate matter sensors, you can use particle counting as one method using a laser beam, and another method would be mass detection, where particles accumulate on a filter band, and then from scattered light you can record the mass concentration of this particulate matter. For gases, we have very different measurement principles. We have the metal oxide semiconductor sensors that reduce the gases on an oxygen layer of a heated semiconductor. And these sensors are very cross-sensitive to other contaminants, and they need gas-specific calibration. A second type are the catalytic type sensors, where a catalytic material that is sensitive to the trace gas is included, and a compensator element, so that you can have the differences between the gas, the measurement gas that contains the trace gas, and another flow that does not contain the trace gas. And so the difference in the resistance can be measured by a Wheatstone bridge and is an indicator for the gas concentration. The third type of gas sensors are the electrochemical sensors. They detect the gas by an interaction with an electrolyte, and they are larger and more expensive as compared to the MOS sensors, but they have very low power requirements and they have very low detection limits. So they have advantages, but a disadvantage is that they have a short operational time. This is about 1 year. And the detection of particular gases is also possible by non-disperse infrared sensors. So they detect the absorbed, or they register the absorbed light from a transmitted laser beam. So the accuracy of these sensors is very important, and I would like to discuss this point shortly with you. The accuracy is characterized by two different measures. This is the trueness and the precision. And you can see it here on the right-hand side on this diagram. We have the reference value here at some point. I hope you can see my pointer. And the average value of the measurements is here, and you have the distribution. And the difference between the reference value and the average value is the trueness. And the scattering around the average value is the precision. So with these red pictures here, you see that low accuracy can occur due to a low precision. All the shots are far away from the target, but low accuracy can also occur with high precision, but with a very poor trueness. in this case. And you can measure all these accuracy parameters by the mean bias error or by the mean absolute error. This is for the trueness, and so because this compares the tests, the measurements with a reference, and the precision is assessed by the difference range in the Blunt-Altman plot. And here in the next slide, I have a Blunt-Altman plot of some noise measurements. Imagine you always measure with a reference device that is a precision device, and then you have your mobile low-cost device, and you measure them synchronously in parallel. So, and of each measurement, the mean value, the average value is on the x-axis here. And the difference between the two measurements is on the y-axis. And so the difference range is this range where the differences scatter around 0. And for 99% confidence, this is a range of the mean plus minus 2.3 times the standard deviation. So when this difference range is very, very large, then the precision is very low. No? I come back here. So a proxy for the precision is the difference range from the Blunt-Altman plot. And from this Blunt-Altman plot, you can also see how this difference range changes with the pollution or with the strength of the signal. So when you have a higher mean value, you can see that it seems to become more precise than for lower values here. And for our measurements, we did an exercise to assess the accuracy of the small wearable sensors. And here's a collection of such sensors. We have some smaller but also some high cost precision instruments, and we compared them pairwise for noise, for temperature, for particulate matter, for humidity, light, and also regarding the GPS signal. We did such a comparison. And the design of this study was as follows. Here we have the standard. This is a reference. Here we used a reference device for particulate matter and for noise and temperature. And then we used test devices. So this was a low-cost particle sampler. And here we used a smartphone app for the noise detection. And also for temperature, we used different devices. And for the GPS, for the geoposition, we used several devices and compared this to the original route that was followed. And the persons indicated their route on a map. So they put all the points on a map where they have been, and then we compared this with the GPS signal that was registered. And this was made outdoors in different city regions, and also indoors in the climate chamber with different conditions. And we also compared the how easily are the sensors to handle. Do they have internal memory, and is the battery power enough? And how long is their reaction time? When, for example, when you come to a junction and there's a high pollution, how fast reacts the sensor to this elevated pollution? So all this we considered, and the measurements in the city in different districts of the city. They were especially important for the geo position, for the GPS. And we compared the smartphone GPS with some other GPS sensors. And yeah, you can see here are some very densely built areas, and we have green park areas, and they have different deviation, different precision. And you can see, especially here in the green park, it's not so precise the geo position like in for example in the built-up area, because the buildings are obstacles against the contact to the satellite. So this impairs the quality of these measurements. And when we compare this to the GPS in the smartphone, we find that the smartphone GPS is highly accurate. And this is because it also connects to the Wi-Fi in the buildings, in the nearby buildings, and this improves the precision of these sensors. For assessment of all these different sensors, for a combined assessment of their accuracy, here you see several plots. On the top right, we have a plot of the noise measurements. The reference is in red, the test device in blue, and they are very close together. So outdoor noise measurements are quite good. We used here a microphone with a smartphone and a particular app that registered this noise, and so this works quite good. And here is a so-called Taylor diagram that displays the different accuracies of the sensors, and the standard deviation here is standardized, so you can compare with this plot all the different sensors, even if they are different and used in different regions, because this is standardized, and so the standard deviation is always set to 1. And this plot also compares, this plot also includes the correlation between the reference and the test sensor, and also the root mean square error of both. I just try. To use another laser pointer here. So you can see here at 1, because this is standardized, at 1, this represents the reference. All the reference instruments, the precision instruments, are represented by this point, and you see the closest test measurements to this point are the GPS devices. So the GPS signal is the most accurate signal. And then you see here some noise measurements, and then the temperature measurements, and the particle measurements are less accurate. Noise measurements from indoor environment are also very inaccurate, and the reason is that in this indoor environment there was very, very low noise, and so it was below the detection limit of most of the sensors. So we can remove this from our consideration, and in summary we can conclude that the precision of the GPS measurements of the GPS sensor is highest, then the precision of the noise, then the temperature, and at least at the end the particle number concentrations. So we have some ranking of the accuracy of the sensors. But anyway, their accuracy is quite similar. It's not so far, so very different. And so that means we can apply them together in one study. So I would like to discuss with you something about the applications of environmental sensors. Such person-based measurements are useful for the collection of exposure data for an individual. So we have cumulative exposure data, we have location and activity-specific exposure increments. So what locations are especially dangerous and where is high exposure, where is exposure lower. And we also can calculate frequency distributions of these exposure increments. And we have some data about the mobility habits of the volunteers and their behavior. And a particular opportunity of such sensors is that we can provide feedback of the exposure data. So some commercial wearable sensors, they are in commercial, some small sensors are commercially available that display, it's like a traffic light, red, yellow, and green. And this depends on the air quality. So when you move with such a sensor to a very polluted area, then the sensor has a red light. When the area is very clean, then it's green. So this strongly improves the environmental health literacy of the participants. And this feedback can also facilitate behavioral changes. So when people know this area is highly polluted, even if they don't smell it, or for example, NO, nitrogen oxide, you cannot perceive directly, but you have the sensor and then you can mitigate these highly exposed regions. The second field of application is excuse me. The second field of application is to explore the air quality of a city and to capture the air pollution variability in a city. So you can see how strongly variable is air pollution in a city. And citizen science can bring a lot of crowdsourced data that can be later on combined with simulations of air quality models. We can plot the data along the trajectories. This is called time geography, and this improves the understanding of the prevalence of the disease, of its etiology and its transmission, and it also supports urban planning. I would like to show you an example here. This is an exposure assessment with the GPS data of individuals. We have here a map of the city on the bottom, and we have the time axis is the vertical axis is the time, and here you have the life trajectory, the life path of the individual where they move, and these different planes here indicate the concentration of the risk factors. So you can you can imagine how an individual experiences combined risks of different factors during its movement in this urban area. And this concept of time geography was developed by Hagerstrand in 1975. And yes, it's a very important tool to combine the exposure data with the behavioral data. And in the next slide, I demonstrate you how this environmental sensing was made here in Leipzig. This is Caroline, and Caroline has a set of sensors as a backpack here. You will see it more from behind later on. And she has a smartphone here on her upper arm. And this smartphone registers the light and the noise and also the position and the movement, the accelerometry. And the smartphone also registers and stores and submits the data. And now he starts. And recordings are taken every minute. Each minute we have one recording. And that means the measurements points have a distance of about 20 meters. So some questions arise here. We can ask what sampling rate is best. Should we sample at a higher rate or less? And in which urban regions should the measurements be made? Should we only measure an individual road, for example, commuting, or should we measure all the day during the entire course and movements of an individual? So the problem is we need some theoretical concept how to do exposure measurements because this can help us design field studies with volunteers. So in the next chapter, we discuss these concepts of personal exposure measurements. And firstly, we have the concept of the microenvironments. Microenvironments are characterize different levels and different combinations of exposure depending on the immediate surroundings of an individual. And so the advantage is that this exposure is associated with the daily agenda in a sequence of pollution patterns. So we are able to assess the approximate exposure based on a person's time activity profile. So when you go to a bus stop, you have a different level of pollution compared to a park. So you just have to have a time activity profile. How long are you staying in the park? How long will you stay at the bus station? How long will you stay indoors? And so on. This concept, however, is insufficient for rapidly changing dispersion conditions and also when the dominant pollution sources change. It is also insufficient for indoor air that varies considerably between different apartments. For example, black carbon exposure was found to be significantly elevated in diesel vehicles, in the subway, or in rooms with tobacco smoke. But some authors in the literature, when they studied PM exposure of school children, for example, they observed relatively high concentrations, high correlations between the mean concentration in the microenvironment of different microenvironments, of the home, from the transit, and from the school. And they realized that there are peaks of concentrations in different microenvironments, very pronounced peaks of concentrations, and they attribute these peaks with health effects. So that means maybe microenvironments is not the best concept for personal exposure, but so far this is not clear, and I think there's still some research required. The second concept is a land use regression. So we assume that under weak wind conditions or as a long time average, there is an association between the urban structure and the air quality. So this is used in many papers, land use regression for air quality. But when you have rapidly changing dispersion conditions, then this is also not sufficient. So wearable sensors gather really the comprehensive data at the place where the individual is. And so wearable measurements have clear advantages. But before you perform such measurements, the sampling design needs to be specified. And especially the sampling rate. I already discussed about this point. When you move with a bike and you have a sensor sampling every minute, so the samples are 20 meters, have 20 meters distance. But what is the best sampling rate? How to specify this? And this depends on the heterogeneous air quality field in an urban area. When the field is homogeneous, it's sufficient to have few points, but for a strongly heterogeneous field, you need many points. So for the specification of an optimum number of sampling points, we learned from the methods that are used to locate meteorological stations. And for the specification of meteorological stations for their location, there's a criterion, and this criterion is a sphere of influence. The procedure is that you calculate correlations between measurements of nearby stations, and this is, you can see here in this diagram. The x-axis is the distance between the different stations, and this is a correlation between the stations. And so the correlation decays with the distance. And as soon as this correlation function crosses around 37%, here we define the sphere of influence. So we have influence within this radius, but outside of this radius, the influence is less. And this is used for the specification of the distances between the meteorological stations. And we applied this same concept to specify the sampling rate of a moving individual with wearables. So we took some mobile measurements with a high sampling rate. For example, every 5 seconds we measured, and we calculated for a buffer of such frequent measurements the correlation function around these points. And you see this here from an example measurement that was taken in 2017. And the dots mark the sampling sites here, but you have between two sampling sites, you have many more sampling sites, and we calculated the correlation function of all these for each point. And then at the cutoff, when the correlation decayed below 37%, then we found the square of influence. And around each point, you can see here a square of influence. And when these spheres, when these spheres overlap strongly, then you have a too high sampling rate. So sampling rate of 5 seconds would be too much, and we realized that a sampling every minute or every 2 minutes would be adequate for this experiment or for these measurements. For sure, this depends on the speed and on the autocorrelation of the air pollution field. And this sampling rate needs also be harmonized with another property of the sensor, that is the reaction time. When you have a measurement here and you move to another place within 1 minute, then the sensor has to react in this 1 minute. It has to quickly react to the change in the concentration. Here you see an example of different temperature sensors. For example, we have a very fast sensor. This sensor is a testo sensor. Here he has a reaction time of 12 seconds. It's a blue curve, and you see the blue curve brings a lot of detail during this journey here when we measure every minute. But when you compare this to another sensor, for example, the Q-track sensor, has a reaction time of 30 seconds. So this one here, it can hardly reflect all these variations. And the sensor tech has a reaction time of 300 seconds. So it was not possible to make reliable measurements. So that means we have to harmonize the aim of a study with the characteristics of the urban environment and also with the sensor parameters. And our suggestion is that prior to each experiments and measurements, a standard operating procedure should be developed. And this should include details about the purpose of a study and the details of the implementation of mobile measurements, flow diagram, how should be measured, and what sampling rate, what start time, and so on. And all the data also need to be synchronized, so they need to have a timestamp and so on. So such standard operating procedure, such working instructions are very essential for high quality studies, especially when you give the sensors to lay people. And such studies, population studies, are called volunteered urban monitoring. And you can see here, Maximilian is starting his measurements at the entrance of our institute, and he carries also a bag with all the sensors here, and he registers. Excuse me, to start. He registers the air pollution and the temperature and the noise during his movement in the city. So when we have all these records, we can ask how we can improve these records. How can we up-value sensor records? And there are three. I would like to mention here 3 different ways. The first one is to combine them with simulations of urban models. The second is to include the perceptions of the participants, of the volunteers. And at the end of my presentation, I would like to give you some information about a recent literature review that we did about the development and application of wearable sensors. So first, some words about the simulation of urban models. High-resolution models are now available to simulate the urban atmosphere, and we can do this at scales of some meters and some hours. But these models are idealized models, and recordings of real values of the atmosphere can clearly improve the value of such simulations. For example, here are some simulations of an urban quarter. You will see how the temperature changes. This is the color. And you also can see how the wind flow is in these streamlines. And for the combination between measurements and simulations, new and very fast procedures need to be developed. And I can imagine that machine learning algorithms and artificial intelligence methods can be very helpful to do this task, to combine wearable measurements with urban simulations. The second point to upvalue wearable records or records gathered by wearables is to register the perceptions of the participants. In a collaborative study with the IIT in Chennai, we did some walking interviews and asked the participants during their journey and wearing these sensors, how do you perceive this exposure? And we see that the perception of air and noise pollution is highly dependent on the context, where the people are, what they see and what they feel. And so the suggestion is the dimensions of exposure assessment need to be extended by the perception. So we have the concentration of particles, we have the temperature, we have the noise, we have the concentration of gas, but we also can have additional parameters, additional dimensions that represent the perceptions. And all the results can be visualized and communicated to decision makers and to urban planners, and they are very helpful for them. In a recent literature review, we searched for publications regarding wearable sensors, pollution and environment. And you see that since during the last 10 years, there's an exponential rise in the number of publications. And when you consider this in terms of the different parameters that are measured, then you see that wearable sensors are mainly applied to air quality. Thermal exposure sensing is still very rare, and multiple parameter wearables are increasingly studied. So this is the recent years here. And this is very adequate to the multifactorial exposure in urban regions. So this is, I think, the scientific community is on the right way to consider this more in detail. And this is a diagram about the sample size, and you see some studies use four volunteers, 4 study participants, but others are using 200 and 300, and they often combine their sensing using wearables with former health studies. And we see that especially particles are widely studied. Only rarely we have measurements of gas, and interestingly, when gases are measured, then the scientists did not measure in parallel the particles, so there are some needs to improve this in the future. So the studies face strong limitations regarding cost and usability issues, but also with a lack of complementary data. You don't have traffic, mostly you don't have accurate traffic data or inhalation rates of the individuals. And there are also limitations regarding the batteries, reaction time. I discussed this with you already. And the impact of wind and rain need to be taken into account. So these studies are so far mostly done with calm and sunny weather. The take-home messages are that there's a strong advancement and development of such sensors, and the development of new sensors is necessary for multiple exposure studies, but also to improve human-computer interaction. And the personal exposure depends on influencing factors, mode of transport, the urban structure, and this should be investigated more in detail. And we also found that there are very few intercultural studies made in comparing the situation in different climate regions, in different continents. So our plan is to develop a proposal for a project to compare this between the different continents. And studies should involve urban environmental modeling and perception as well, and as also the behavior of the individuals. My nearly final slide is a summary. We argue that the sensor parameters and the environmental conditions should be harmonized, and we have need to do more research with the design of such standard operating procedures and with data assimilation techniques to bring together simulations with measurements, and also to investigate aspects of the individual behavior. At the end, I would like to thank our partners who cooperated with us, and this is my colleagues at the Helmholtz Centre in Leipzig, but also the University of Leipzig, the psychologists there, and especially Professor Shiva Nagenda at the IIT Madras for these very interesting studies and comparisons of the different sensor designs, and also with Heike Marquardt from the German Aerospace Center, who did a lot of measurements. And at the very end of my presentation, I would like to show you some impressions from our last measurement campaign. This is a city from Leipzig from above. Leipzig is not so very big as compared to Chennai. Here you can see how we equip the volunteers with the instruments, and they measure on their daily routes. So we have not pre-specified routes, but we use the routes they normally commute every day to their working place, but also the routes where they go for shopping and for some sports. And so we have not only the exposure data in these areas, but we also have their behavior, and we ask them whether they would like to change the behavior due to high pollution concentrations. And so we would like to study the human computer interaction or human sensor interaction during these studies. So I thank you very much for your attention. Apologies for some disturbances in between. Yes, I'm open for questions now.
Yeah, Professor Schlink, thank you very much for the wonderful talk. It was very, very good, and a lot of learning in particularly the new set of sensors that are being used in many of the cities for air quality measurements and also personal exposure. So there is a chart box. Are you able to read the chart? Because Sharath has asked some question, or you want me to read it? So just if you are comfortable, then you can go ahead with that.
Yes, I can see this chat.
So,
and there's a question.
You can see that there is go ahead.
There's a question about the sensitivity of particulate matter sensors to high temperature and humidity. And yes, I can agree to this. Especially with high humidity, this is a sensor. One subject or one point is a sensor that the sensors are cross-sensitive to other pollutants, but as you mentioned here, also to humidity and temperature. And especially with high humidity, you have the effect that the particulate matters agglomerate when humidity is high. And so already in the air, there are some processes that change the number concentration of these particles. Yes, but I think we all realize that they are so cross sensitivities, but I think they are less specified in quantitative terms. So when at the moment we are calibrating some of these sensors, and in the equations to calibrate these sensors, we also include temperature and humidity to account for these effects. But this is just an approach to handle this somehow.
Thank you, Professor Schlink. There's another question. I'll read the question. If the passive samplers are not feasible for many reasons, then is there a way to calibrate the sensors? That is the first question. I think there is a question in your chart box. You can look at it. And the second question, can we compare it with some other automatic instrument in a stationary condition? And then which location of sensors on the back or a front will be technically feasible? Will there be any significant difference in readings? So, I mean, just to try to put you, so where to keep these sensors in order to get a reliable readings? Should we keep it on the back? Should we use them? Because all this aerodynamics will have an influence in, in the measurements.
Yes, I think the best location would be on the arm and on the back, that the sensor is not so influenced by the human body. And yes, but if there is strong sunshine on the back, then the sensor is influenced by the sun. So each sensor should have a sun protection and also some ventilation. And yes, I think we should design the sensor carefully that becomes that it's less sensitive to the location where you have it on the body. And I think an active sampling, I mean by active sampling, I mean then the sensor is ventilated. This is very important for the sensor to be very fast, because there is a first question. The first question is about the passive samplers. And because the passive sampler does not register in a high temporal, registers the data in a high temporal resolution. For example, when you move in the city and you have some passive sampling. Passive sampling also means, for example, there's a, I showed you the plot of the sensor tag. This is a temperature sensor. This is like a coin, but it's not ventilated. It's like a coin and it samples the temperature. So when you have this temperature sensor and you carry it with you and there's no ventilation, then it's too inert to register quick changes in the temperature. And I think the same is valid for passive sampling of air pollutants.
Mr. Schlink, I have one question from my side. Okay, are there any other questions? Participants, please use the chat box. You can, yeah, there is an interesting question. The traffic data, can we use Google traffic data as an air pollution index, as it is very accurate? So, I mean, what's the, people are saying that over a period of time, the repeated measurements might have been in providing the Google much more accurate data. Can we use the Google traffic as an accurate data to predict air pollution index?
Yes, this is a good suggestion, and we try this already. Because as I showed you, we should combine the simulations, model simulations with wearable measurements. For example, it is important when you have a volunteer and the volunteer moves around the city, and it turns out that this route is highly polluted. Then you should make a recommendation to the volunteer to take another route. And when you, for this recommendation for an improved route with less pollution, you should have traffic data to know how is the pollution in general less. So, and for that, yes, for that person, for that purpose, these traffic data from Google Traffic are very important and helpful.
Okay, so there is another question. I think the previous question was from Imanshu. I think you may be knowing it, our student Imanshu. Okay, the next question is from, how frequently should the sensor be calibrated? Are there any standards? Is there some guidelines available in Germany?
No, there are guidelines, but these guidelines are specific to the sensors. So each type of sensor has a different guideline, how often it should be calibrated. And this year we bought some sensors and used them with their calibration, but we also tried to do our own calibration, and there were some differences. And so I suggest that at least before a study and at the end of a study, you should make a calibration of the sensors to see how strong they drifted during this time and what changes occurred there. But as you also realized in my presentation, some sensors have very short lifetime. So after 2 years, for example, you cannot use them anymore. So this depends on the sensing principle, and so yes, these sensors are mostly low budget sensors, and so we should respect this low budget property, and so then we should buy new sensors or recalibrate them. So it's not so stable like high precision sensors, for sure.
Shrink, there's a follow-up question from my side. In many countries, there is a lot of changes happens in using this, particularly this affordable sensors. I don't also wanted to call it as a low cost or a low budget. Maybe we will try to look at this as an affordable sensor. So there is a lot of exchange happens. Should we use this many sensors? Because again, if you use so many low budget sensors, and if you put the numbers to be quite large, then its cost can generally increases several folds when compared to a sophisticated monitoring station. So, is there any plans in Germany where I've noticed that maybe you have set up some of the continuous monitoring stations, and particularly in the low emission zones to designate? Is there some plans for you from the government side to use these sensors for the air quality management, or to bring some compatibility with the conventional air quality monitoring sensors or station?
Yes, this is an interesting question. I think this is not. I think this is not planned, and I think it's not possible. The reason is we can use affordable sensors for research. This is okay. This is fine. But the monitoring of the air quality in cities is a governmental task. So the government has some. There are also some legal regulations. What is the level, the acceptable level of air pollution in the city? So, and currently we have, or last years we had some problems with nitrogen oxide levels in cities, and also particulate matter in some cities, because they exceeded the levels of the European specified by the European Commissions, and this has some consequences that the countries have to pay some a price for this high level.
Yes.
Yeah.
Compensation.
And the affordable sensors are not approved to have an accuracy to do this task, and so the government is still skeptic against the use of such sensors. We can use them for personal exposure measurements and for research. This is clear, but we cannot replace the official monitoring stations in the cities.
Okay, yeah, that's a very interesting inputs, Professor Schlink. There's one more question. I think Himanshu has come back again. As machine learning and AI are boom, can we calibrate affordable sensors with high-cost sensors, and then use these affordable sensors, which will help in cost cutting?
Yes, sure. It's a way to do this, but the affordable sensors are not stable, not very stable in their values. These measurements change during the time. They drift to lower or higher values. So I think this can be done, this calibration with high cost sensors during a short period, and then they have the affordable sensors measure in very good precision, but in long term it will not be helpful. But anything, I believe that artificial intelligence methods are very helpful to combine all the data gathered with the mobile sensors with the simulations. And because when many people use these wearable sensors, you have a lot of data, and I think this is a very good database for combining with simulation data.
Yeah, thanks, Prof. Schlink. I think you have made particularly this wearable sensors many informations which will definitely, I'm sure that many students will motivated to take up further work on this direction, because this is an upcoming area. So before we'll say thanks to you, I request all of you to start your camera. We will request Dr. Madhusudan to make an official vote of thanks for this particular lecture series. So Dheeraj is here, Prof. Schlink, so you can just say hello.
Hello, Professor.
Congratulations.
Thank you. Thank you.
Karyachat, good evening to you. Schlink, is it, I think Professor Karyachat is interested. We can do some similar work in Thailand. Maybe we'll explore that one. We'll have another meeting with him. We'll see.
Yes.
Yes. Would be nice.
So can you all quickly start your camera? Dheeraj, will you take a photo?
Yes, sir. I'll take. There are still many people are yet to switch on camera.
Yeah. Okay, we'll just wait. Gopika is not visible.
I'm taking pic now, sir.
Okay, go ahead.
Done, sir.
So once you finished, you said.
Sir, it's finished. I've taken picture.
Done? Okay, thanks,
Sir, can you hear
Dheeraj.
me?
Now I think.
Yes, sir. Yes, sir. It's done.
Okay. One minute, some phone call. Yeah. So, Dr. Madhusudan, I'll request Dr. Madhusudan to, formally say vote of thanks. Yeah, on behalf of Air Quality Management lecture series, we would like also to congratulate Dheeraj to become, to receive his doctorate today. Maybe he defended his thesis today. Yeah, Dr. Madhusudan, over to you.
Yeah,
maybe we can make.
Thank you, sir. Thank you very much.
So I think we will start with a happy note. Congratulations, Dheeraj. Today we also completed our 12th edition of our monthly lecture series. And I take this opportunity to thank all CEPHA partners, directors and co-directors to happen this event without any break. If you look into the speakers and their background, the terms of experience and domain knowledge, one can see that all were gems of personalities, and the participations were always around 80 plus in all the lectures. This shows how popular this lecture series is, and the gist of the lectures and the video recording were available in our CEPHA website. One can always browse into and look into. Coming to today's lecture, Professor Schlink is always supportive to CEPHA network and always available for all technical discussions. So the topic today was the individual wound sensors assessing personal environmental exposure problems and perspective of wearables. The discussion focused on 6 aspects, that is the motivation and problems, the technical informatics, the accuracy, concept, the implementation, and the perspective and outlook. Professor has introduced a new concept, that is Exposome. Exposome is nothing but putting environment into genome. He has explained the issues of urban problems, the chronic diseases, and the dynamics of lifelong environmental impacts and the environmental chemical substances. So with that introduction, he has moved to the activity and behavior, how the sensors are working, how the sensors can be tracked, and how the sensors are accountable. So further, he explained about the assessing the particulate counting and the gaseous monitoring through the sensors. And he explained through the classical chart about the accuracy, the trueness and precision chart, the performance assessment of these test sensors and references were compared. And he explained the exposure assessment with the GPS data of individuals. So beautifully explained how the people do the measurement and the concepts of personal exposure measurements, the microenvironments, the land use regressions, wearable sensors and its applications of measurements were explained properly. And the lecture ends with the implementation part, suggested for having the importance of having the standard operation procedure, which will enhance to gather the data of urban air quality. And he emphasized the need of artificial intelligence and machine learning program into the sensor data, the limitations and harmonizing the need of the sensor measurements were further explained. And after an hour-long lecture series, with different questions were answered properly. The clarity were quite good, and we thank Professor for his valuable time. And definitely, our group will be enriched with the knowledge and the new concept of the sensors technology. And on behalf of CEPHA network, we thank Professor for delivering this technical session. And we also thank our colleagues, our partners, and also the regulatory agencies participants, State Pollution Control Board participants, senior professors from different IITs, and also the students who supportive enough for attending the entire session. The thanks are also due to to Swaroop, Gopika, and Dheeraj, who supported the activity from the back end. We thank Professor Shivanagendra for all his guidance and supportive. And definitely we will meet for the next month for the next edition of our air quality monitoring lecture series. Thank you, everyone. Thank you.
Yeah. Thank you, Dr. Madhusudan. Okay, Prof. Schlink, thank you very much. So enjoy your evening and namaste. So thanks to all the participants, all the professionals. Hope at least after some months, we will have in presence of air quality management lecture series, and also with a combination of maybe kind of an hybrid. Yeah, thank you, Prof. Schlink. Thank you, Dr. Madhusudan and others for making this lecture series interesting. Professor Schlink, see you. Bye-bye.
Bye-bye. Thank you very much. Bye-bye. All the best.